finite dimensional vector space. V is known as dimension of vector space V, and it is denoted by dimension V. So, dimension is nothing but the number of vectors in a basis of that space, and the basis is just a set of vectors that are linearly independent and can be used to create another set of vectors of that space. So let's see the example of a dimension. Example first is S equals to V1, V2, V3, V4. V1, V2, V3, V4 are the elements of basis V of matrix of M2. Here M2 is a matrix of 2 by 2, and the dimension is denoted as dimension of matrix. Dimension of S is equals to 4. Here dimension is nothing but the elements of basis. Let's see the second example of dimension. V equals to R square of S equals to the elements of R square are 0, 1 and 1, 0. The dimension of R square are 2 because there are 2 elements in vectors in basis of S. So the dimension of R square equals to 2. Example 4. V equals to R cube. Let's see the elements of R cube as S equals to 1, 1. Elements of R cube are 1, 0, 0 and 0, 1, 0, and therefore are 0, 0 and 1. So as we see, the elements of vector space R cube of 1, 2 and 3. So the dimension of R cube is equals to 3. Let's see the example 4. The M22 is nothing but the matrix of 2 by 2, and the matrix of 2 by 2 element equals to A, B, C and D. Here we say that the of 2 by 2 matrix. So the elements of 2 by 2 matrix are 4. Therefore, the dimension of by 2 matrix is equals to. Remark for this example is if S equals to V1, V2, V3 of V of n of finite dimensional vector space V is a set in V with exactly n vectors, then every set in V having more than n vectors is linearly dependent. Every set in V having less than n vectors does not span V. So as we say, the vector, the dimension is nothing but the number of vectors in a basis of the number of vectors in a basis of that space, and basis is nothing but is just a set of set is it's just a set of vectors that are linearly independent.